So the other day when I was building my Qid for ColdFusion implementation, which is a ColdFusion port of the Qid library by Eric Elliott, I had to create a thread-safe counter, meaning I had to iterate over a range of numbers and then reset the counter back to 0, but I had to do that in a thread-safe way because ColdFusion is a multi-threaded environment. Now, because I wanted to try and avoid locking in my code, I ended up using Java's AtomicInteger, which is part of their atomic data types. And I thought that was a pretty interesting use case, so I wanted to try and extract that out into something, maybe more as just a mental note to myself, but I ended up creating a ColdFusion component here called atomic range, and atomic range is essentially a counter that iterates over a set range of numbers based on a lower and an upper bounds, and then resets that range back to the lower bound when it hits the upper bound, and of course doing this in a thread-safe way. So to initialize, here we can take a limit 1 and a limit 2, and if you provide both of these, the min and max become the two provided limits, and of course if you omit the second one, I treat the provided limit as the upper, and then I use 0 as the lower. Now, this class is pretty simple. Under the hood, it's just using, again, this atomic integer out of the Java util concurrent atomic package, and I initialize it with the lower bounds there. And the method really exposes next to no functionality. Essentially, it exposes a get and increment, or an increment and get, and internally these are just calling increment and return, and this is really where the meat of the entire component comes into play, because this is where we're going to manipulate the atomic integer itself. Now, the entire atomic package is really based around this concept of compare and set. Let me scroll over here. The compare and set method essentially takes a precondition and the value that you want to set into the particular data type. So in this case, I want to set the next value of the counter, but only if the current value of the counter matches this known value. This compare and set will return a Boolean value. It returns true if the next value is able to be set into the counter, and it returns false if it wasn't because the current value didn't match. So if we look at this loop, what we're actually doing is just looping forever. So while true, this will loop forever until we break out of it, and we're going to break out of it essentially by returning inside the loop, but only if our value gets set. So let's just take a quick look at this logic. So we're looking at the atomic integer, we're getting its current value, and then we're adding the range steps. We're either going +1 or -1 depending on the direction of the range. And at this point we need to check to see if we've reached our upper limit of the range itself. If we're counting up, we check to see if the value is greater than the max, and if it is, we go and reset back to the range min. If we're counting down, we essentially do the same thing, but we reverse the greater than less than sign. So here's the logic where we're actually performing that, that resetting of the integer inside of the range. And again, I then go to set the next value, but only if the current value is still the current value, because this can be called, and again, in a multi-threaded environment under a lot of contention, it's possible that another thread came in and actually changed the counter value while I was performing my range logic, and if the current value isn't what I expect it to be, then this simply returns false, which means that our while true loop iterates one more time, and again I just continue to do this over and over and over again until I'm able to set that value. And this essentially allows us to create a thread-safe range without having to add any additional locking in our code, because the atomic class uses sort of machine-level lock operations, which are much more efficient. Now to test this, I'm going to create an atomic range, and here I'm going from 1 to 10, and then I'm going to spawn a number of CF threads here, and inside of the CF threads I'm going to call the get and increment method a whole bunch of times. So I'm going to have 11 threads, and inside each thread I'm going to call the increment method or some form of the increment method 173,000 times. So because we know the thread count, we know the number of times the increment will be called, we can then calculate what the expected value of the range will be after all those operations have taken place. And here you can see at the bottom, we're blocking until the thread completes, and then we're just checking the current value of the range against the expected value. And if we jump over here into the browser and let's just refresh, and you'll see that we're just waiting for the loop to complete the 1.9 million iterations. It's done in, let's see, can you see the time here? In just under 6 seconds. And you can see the expected value is 9 and the actual current value of the atomic range, or sorry, expected value is 8 and the actual value is 8. So we landed exactly where we expected to, which means that the mutating of the underlying atomic integer was performed in a thread-safe manner, and we didn't get any lost increments or decrements in there. So anyway, more of just a note to self, I suppose. But I don't know. I think that the atomic package in Java has some pretty interesting stuff in it. I've really only used it a handful of times, but performing experiments like this makes me want to go back and dig more deeply to see if there's more magic that I can leverage in that package.